Okay, so we last term we dealt with chapter 1, the multivariable calculus chapter. So there's 2 chapters to do, which we're going to do. 2 chapters remaining, which we're going to cover this term. Chapter 2 on the Laplace transforms, which for us is going to mean a method for solving certain differential equations. And then chapter 3 on Fourier series, which is a way of decomposing a large class of functions in a standard way, representing functions in a standard way as a infinite series of sine and cosine. So looking at chapter 2, so what we're talking about is differential equations, ODEs, things like this here. You see at the bottom here in equation 2.1. So this is a differential equation. It's an equation concerning the unknown function y, let's say. And it's called the differential equation because it features various derivatives of y. And the main aim that we're setting ourselves here is when faced with one of these equations is being able to solve it, okay? Being able to find a description of the function y which satisfies such an equation. Now, there are many different techniques for solving differential equations. Certainly, we should say that they divide into 2 main camps called analytic solutions and numerical solutions. Not all differential equations can be solved neatly and nicely on the page to produce a kind of nice formula for the solution. If they can, then that's kind of called an analytic solution. If you can kind of do some symbolic algebraic manipulation of the equation, go through some procedures and produce a solution which is expressed in terms of kind of standard functions, polynomials, trigonometric functions, exponentials, logarithms, those kind of things, then that's kind of called an analytic solution. You find the solution exactly. But many differential equations don't have such nice analytic solutions, and they're, in order although the solutions to them exist, mathematically, they can't be described so nicely. So for those kind of equations, you have to solve them numerically, which is using numerical algorithms, computational algorithms that you use to estimate values of the solution function. Okay. Now, you'll be learning about numerical solution methods in Norman's lectures in the Introduction to Numerical Methods course, and further in the 3rd year courses on ODEs and PDEs. Okay. But what we're going to learn about here in chapter 2 is a certain method for finding analytic solutions. Okay, solutions where the solution is described using in terms of combinations of standard functions that we know about. So a bit of terminology. So I talked about differential equation. We call it an ordinary differential equation if the unknown function is a function just of a single variable. And so these derivatives are just the normal standard single variable derivatives. On the other hand, we have a partial differential equation. A partial differential equation is where the unknown function is a function of 2 or more variables. Okay? And so the various derivatives that may be appearing in the differential equation are partial derivatives. Okay? So that's called a partial differential equation, or PDE. Okay. Now, differential equations occur all over the place. As soon as you start to mathematically model any kind of real-world process in science and engineering, invariably they tend to, especially any kind of process that's changing through time or anything, they tend to be described by differential equations. Okay, so they're very, very widespread in all the sciences. Now, the particular class of differential equations we're going to be looking at are so-called linear ordinary differential equations with constant coefficients. Now, that means a few things. constant coefficients, easy enough to describe. So these coefficients AI here that are multiplying the unknown function y and its various derivatives here, we require those to be constants, okay, just fixed numbers. We will allow a non-constant term in the differential equation on the right hand, so to speak. So the term in the equation which doesn't involve y or any of its derivatives, this we will allow to be a function of t itself, function of the variable itself. But all these other coefficients, the a0, a1, up to an, those are going to be constant coefficients. The term linear, well, it's easier, maybe we'll say what nonlinear is. So nonlinear behavior is where, it's written down here, is where some of the derivatives of y, these things appearing on the left, or indeed y itself, if any of them are raised to a power higher than 1, or indeed if different ones of them, different derivatives of y are multiplied together, that's nonlinear behavior. So for instance, in this one, we see the unknown function y multiplied by one of its derivatives, dy dt. So this kind of behavior is what we call nonlinear. Okay. But if in the equation we see a bunch of derivatives of y, none of which are multiplied by other derivatives, and none of which are raised to any power, okay, apart from just the power 1, so to speak. If that's the case, then we term the equation to be a linear equation, a linear differential equation. So the class of things we're going to be looking at are so-called linear ordinary differential equations, and they are all our instances of this general form here. Okay. The degree of the equation is the highest order derivative that we see. So this equation here has degree n. Okay, just looking over the page, just a bit more terminology. In general, a solution to this kind of thing, there may be more than one solution to such a differential equation. Indeed, the typical situation is that there's a kind of a family of functions that solve these things, which may be parameterized by various parameters, various constants in the solution. So there might be a single unique function y that solves this. Very often, the solution space, the possibly large solution space of such an equation is narrowed down, and often narrowed down to a single unique function by the provision of extra information. Okay? So you think of the ODE as giving you information about the function y. It's telling you aspects of how y behaves, because y and its derivatives have to be in this relationship. Well, we can get extra pieces of information that come in the form of so-called boundary conditions or initial conditions. Okay? So a boundary condition is extra information about some of the known values of the unknown function y at certain points in its domain. Okay? So that's generally called boundary conditions. If the unknown equation y, if it's a function of a time-like variable t, then very often these boundary conditions are in the form of initial conditions. Okay? So an initial condition is information about what the value of the function is at the starting time, which is conventionally taken to be t equals 0. Okay? Time runs forward from the present moment, so t equals 0 is the starting time, and then the time runs forward. And so if you have information about the function y, if you know what its state is at time 0, that's called the initial condition of the function. And there may be other initial conditions, not only about y, but also about some of its derivatives as well. Okay. So that's just some other terminology. Now, before we meet the Laplace transform and start investigating how to solve these equations, we just want to give a bit of just a very quick overview of what the kind of solution process is. So we're going to have this thing called a Laplace transform. And what that's going to do is it's going to take the original differential equation, the kind of thing you see in 2.1. It transforms the equation into a different setting. Okay? And it takes your differential equation and it translates it into another domain. And it's one where all the derivatives disappear. And instead, they're replaced by certain algebraic operations that are kind of easier to deal with. So we transform the whole problem into an easier one, a conceptually easier one to solve. Then we solve the transformed problem. So we end up with a solution to the transform problem. And then we do the inverse Laplace transform. We bring our solution to the transform problem and translate it back into the original context to recover the solution to the original ODE. Okay. And so before we get into it, I just wanted to give you some motivation for that, or just describe a kind of an analogous situation to that. Okay? So this is thinking about transforms in the context of something you already understand. Okay? So I want you to imagine the world before computers, calculators. Okay, it's not that long ago. So, we've obviously been doing maths and science for a very long time, long before there were any automatic calculating machines. Okay. So how did people do numerical computations? Or what kind of tools did they use? What tools did we use for computations before we had computers or calculators? If you think of one of the coursework problems that I had set you, what was it, 1.97 to the power of 2.01? Now you just type it into the computer gives you as detailed and as accurate an approximation to that as you might want. But what would you have done with that 100 years ago? How would you have worked with that? Okay. So a transformation or a transform that was used was the logarithm. Okay. Because certain operations might be considered hard. So raising one number to the power of another, if their number is in decimal form, not small integers. Small integers you can do power, but if they're numbers with detailed information, how do you do these calculations? So that's kind of hard. And maybe a little bit easier, but still considered hard, is how do you multiply together numbers? Okay, we learned in primary school how to multiply together numbers, but if you've got long decimals that you want to multiply together, it's still a very time-consuming process if you were to do it by hand. Okay. Well, there's the transformation of the logarithm. Okay. Now, what happens when you transform a to the power of b by the logarithm? Okay. Well, you take the logarithm of a to the power of b, but we know from our theory of the logarithm, properties of the logarithm function, that the logarithm of a power like this is the same as b times the logarithm of a. Or if you take the logarithm of a product, everybody knows that that's the logarithm of a plus the logarithm of b. So these problems are, well, in comparison to what they were, the problem here, or the computational task here, is easy, or easier. It is easier to multiply together two numbers than to raise one to the power of the other one. Similarly, I would much rather simply add two numbers together than go to the trouble of working out their product. Okay? Doing a sum is an easier task. It's physically easier than doing a product. Similarly, multiplying together two numbers is less intimidating, easier to do than the original problem of figuring out a power. So, you know, given a problem like this, you might work out its answer. Let's just call it n, or m, whatever the answer to that. Now, but these numbers n and m are not the solution to your original problem. They're the solution to your transformed problem. But if these are the quantities you're interested in, there is an inverse transform. What's the inverse of the logarithm? The exponential function. Okay? The exponential function. So what you do is you apply the logarithm, you do your computation there, which is easier. You get these values n and m. But then to recover the answers to a to the power b and ab, we simply take the exponential of the answers we got here. So providing we can do it, providing we can apply the transform of the logarithm, we can take these hard computational tasks and convert them into easier computational tasks, which we could then carry out using whatever methods or by hand or whatever. We get answers to the transformed problem, and we can get back to answers to the original problems by applying the inverse transform. Okay? So we have this hard domain. We apply a transform, we're over in an easier domain, and solve problems there, and then do an inverse transform. And this is the reason that we have things, tables of these numbers. So if you So not this kind of thing, but this kind of thing. In fact, let's even type in old log tables. Okay, this kind of thing. So these things were around a long time ago. I'll fess up, I make that joke every year. Every year it's kind of funny, but okay, the detail there isn't too hard. So okay, you can recognize it's yellow paper. So people tabulated values of the logarithm function. Let's see if we can get a better example. Oh,
The shopping center.
So these are just some stock photos. But so these things have been around for a long time, okay? Hundreds of years ago. People tabulated values of the logarithm function, and they also tabulated values of the exponential function. Now, of course, they've been superseded today by the use of computers, of course. But before computers were available, log tables and their corresponding exponential tables were a common computational tool that were used in order to carry out mathematical computations. So the procedure would be, if you were doing lots of computational work, okay, you were working with quantities, accurate quantities with decimal places. If in the course of your calculations you had to perform a power like this, you would use your table to look up the logarithm of the base, okay, and then just simply carry out this multiplication. You'd obtain a value n, then you'd get out your exponential table, you'd look up the value n, and work out what its exponent would be. And that gives you an approximation then to the value a to the power b. Similarly with products, if you have to multiply together two numbers, to do it quite quickly, just get your log tables, look up the logarithm of a and b, add them together, and then look up the exponential of m, and then you get your value 2 a times b. So the Laplace transform, whatever it is, we haven't said anything about what it is yet, but the Laplace transform does a similar job for solving certain types of ODEs, okay? Those linear ODEs with constant coefficients. Okay. We're not going to solve the ODE directly. We're going to first transform it into a different domain and work with the Laplace transforms and solve the equation in terms of its Laplace transforms. And then at the end, carry out an inverse transform to obtain the solution to the original problem. Okay. And indeed, just like those log tables, we have our own tables that we're going to be using. So if you go forward a few pages, where's my notes gone? If you go forward a few pages in the notes, we've got our Laplace transform table. Okay. So you can see, just like the logarithm table, it lists a load of common functions of t and lists their corresponding, what we're going to learn about now, their corresponding Laplace transform. So we'll be using this table to carry out our Laplace transform and carry out the inverse transform as well. Okay. Okay, so what exactly is it? Okay, we've talked about it. We've drawn a connection with the logarithm or an analogy with the logarithm and the exponential. But what exactly is this Laplace transform? Okay. Well, it's an operation that we do to functions. Okay. So the Laplace transform is something that we apply to a given function. And the normal notation we use is that we have t as the variable of the function. And we tend to think of t as a time-like variable. And what it is, it's some kind of operation you do in the function, and you get a new function, okay? Which we typically, or one way of representing is we use a lowercase letter for the original function x, and then the uppercase version for the transform. It's a new function, capital X, associated to the original function, but it's a new function, a different function, and it's a function of a different variable. It's not a function of the original variable t. It's a function of this new variable, which we're going to call s. So in general, that's what we call a transform of a function. Some kind of rule for taking your function and associating some new function of a new variable to it. There's a whole bunch of different transforms. But the one we're looking at is the Laplace transform. And here it is. It's typically, okay, there's a whole bunch of different notations that we can use for it. I want to expose you to all the different notations that you might encounter. So the Laplace transform of an original function, little f of t, typically you'll see it denoted by these notations. We can use a curly L to denote the Laplace transform. So curly L of a curly brackets of f of t. That's the Laplace transform applied to f. Or sometimes it's denoted capital F of s. Or sometimes people put some kind of annotation on the original function, such as a bar, f bar of s. Okay. Those are various notations for the Laplace transform. But different books, different sources will use different notations, but those are some of the typical ones that we see. Okay, so what is it? What exactly is it? Stop beating around the bush. Show us. Okay, this is what it is. Okay, it's an integral. We basically integrate the function. We integrate the function starting at 0 and through the whole of its domain. So we integrate it from 0 to infinity, integrate the function f, but we put in this extra factor here, this exponential factor. And here is where the new variable appears. So it's e to the minus st multiplied by f of t. Okay, so this is what we call the Laplace transform of the function f. Now, why this should have any connection with differential equations, or why this should be any use for when you're trying to solve differential equations, is not immediately apparent. Okay, it's not apparent to us yet. Okay, but we'll discover the link that this has, and the reason it's a good thing to do when you're trying to solve a differential equation. We'll discover that in time, in due course. Okay. So before we look at some examples, let's just say something about the definition. So here we have the Laplace transform of f of t is this integral. Now, okay, this looks okay. It's an integral of f multiplied by an exponential. But we notice that it's an integral of f over an infinite range. Okay. So does this integral converge? When you're faced with integrals over an infinite domain, that's maybe a question you ask yourself. Is this a sensible definition? Well, in general, integrals of whatever, integrals from 0 to infinity of whatever, converge if the integrand, the thing you're integrating, integrand, which is this, if the integrand gets small fast enough. That's the general way to think about it. Integration is a kind of a summation. You're adding up all the values in the function. You're adding up all the weight that's there in the function. Or if you think about it in terms of the graph, you're looking at the area underneath the graph. For a positive function, you know, the integral is the area underneath the graph. Now, if your function is, you know, hanging around in the upper, you know, is hanging around at large values, you're clearly going to have a infinite area underneath the function. Okay. So if this kind of large behavior continues, we wouldn't expect the integral of that function to converge, because there's going to be an infinite area underneath it. But if the function function has some kind of behavior where it's getting smaller and smaller, then we might expect the infinite integral to converge. Okay? Because although this area underneath the curve might be spread across an infinite width, but if the function is decreasing fast enough, there's a chance that there'll only be a finite amount of area there. There's a chance that the integral will converge. So this kind of thing might converge. This drawing, this probably doesn't converge. You know, if this large behavior of the function continues. Now, in the Laplace transform, the new variable s can actually be complex. Okay, so s will actually be a plus ib. Think of it as a complex number. So what is the size? What is the size of the integrand, e to the minus st f of t? Well, the size of it is we look at its absolute value. Now, absolute value is multiplicative. And what we want to look at is how the size of the exponential depends on its real and imaginary part. Okay, so this is going to be the absolute value of e to the minus a plus ib t. Well, now you see you can break this apart as e to the minus at times e to the minus ibt. Okay, so if your s is complex, it's expressible as a plus ib. And using the rules of indices, that will split as the product of e to the minus at multiplied by e to the minus bt. Now, e to the minus bt, e to the I times something, remember, is a point on the unit circle in the complex plane. That's magnitude 1. Okay, because it's a point on the unit circle in the complex plane. It's that angle theta. E to the I theta. Okay. So this part here has absolute value 1. F of t has whatever absolute value it has. So then we've got this exponential part here. Okay. So the size of e to the minus st is all about how big a is, or it depends on a. Okay. It doesn't depend on b. Whatever the imaginary part is, that's just going to generate a factor of magnitude 1. So the magnitude of this exponential factor comes down to the real part of a. So the integral can converge as long as e to the minus at, which, I mean, what is e to the minus at? T is going from 0 to infinity, okay? So t is getting large. So as long as a is positive, this factor is going to converge to 0. As long as e to the minus at converges to 0 fast enough to make e to the minus st f of t also converge fast enough so the integral can converge. So we do expect we might expect, in general, the Laplace transform, e to the minus st f of t dt, this integral, to converge for a large enough a, which is equal to the real part of s. Okay. So as long as the real part of s is positive and large enough, that will mean that the factor e to the minus at is converging to 0 as t goes to infinity, because it's e to the minus something positive that's getting larger, so it'll converge to 0. And as long as a is big enough, we might expect the convergence of this factor to 0 to drag the whole thing down to 0. Okay. It will converge for functions f, and the terminology is exponential type. So for functions f which are of exponential type, and what this means is, i.e. eventually dominated, meaning less than, some exponential function e to the minus at. A is some positive number. I think I called it lambda in the notes or something. But so there will be a large class of functions f. Those ones, because remember, the exponential e to the positive at, that grows very fast. Exponential functions grow very fast. And conversely, e to the minus at converges to 0 very fast. Remember, e to the minus at is 1 over e to the at. So there will be a large class of functions f, those that are eventually dominated by some exponential function. So I'll take the minus sign off there. The functions f that are eventually dominated by an exponential e to the at, meaning that they're less than e to the at. Then, because you've got e to the minus at present in the integrand, that factor will drag the whole thing down to 0, and so that will allow the integral to converge. Okay. So this is our thing, which is the Laplace transform of f of t. So it's some kind of device that's going to operate in a way similar to the logarithm that makes certain computations easier. Turns powers into products and turns products into sums. Well, the Laplace transform is going to do some kind of a similar job when we apply it to the whole ODE, to the whole ordinary differential equation. And it's going to convert it from a differential equation into an easier kind of equation to solve. It will no longer be a differential equation. It'll instead just be what we call an algebraic equation. Okay, so there won't be any derivatives anymore. There'll just be various functions and various polynomial parts, which we'll be able to deal with using normal, straightforward algebraic manipulation. Okay. So I'll pick this up in our next lecture. We'll start next time. We'll return to this definition. We'll look at some initial examples and then start to look at the properties that it has. Okay?